So, what is the problem with ozone layer thinning? The big problem with ozone layer thinning is this thing called CFCs. CFCs stand for chlorofluorocarbons. And what basically chlorofluorocarbons are is they're compounds made up of chlorine, fluorine, and carbon. So the formula for like a common CFC is here: carbon, two chlorines, and two fluorines. They're 100% anthropogenic. They're a man-made substance. And what they found to be really amazing about them is they're very stable. They do not break down, which is great because they put this coolant in air conditioners or refrigerators. So it's kind of, if you look at the back of a refrigerator and see kind of those like kind of the tubes kind of going back and forth, in there are what's called a refrigerant, which are essentially traditionally in the past have been CFCs. And they're stable and they don't break down. So you don't really have to go replace your refrigerants very often. So this has been a really helpful innovation. And if you think about refrigeration, the fact that we can buy a bunch of stuff and have it frozen or keep it in our refrigerator, you don't even think about, but that's actually a huge innovation in food production and shipping and distribution and storage. So it's actually been really huge. It also, CFCs are used in the production of computer chips. They're like cleaning solvents, and they've been used in the production of styrofoam. So CFCs, 100% man-made substance, and they are kind of causing issues. They're extremely stable. In fact, if you look at this image here, it says kind of right over the little triangle where it says steel. It says contains no CFCs or other substances. Again, it was used in aerosol cans as what was called a propellant, or you see also that logo says like no CFCs. So big idea. CFCs were used a lot in aerosols as refrigerants and things like that. So CFCs came onto the scene. Different sources of CFCs, again, are making styrofoam, in the production of computer chips as cleaning solvents. Big one, again, is refrigeration for air conditioners, refrigerators, freezers, and then in aerosol cans as propellants. Basically, what happened then? What happened to disrupt this cycle is this is a CFC. It's very stable. So it gets into the atmosphere and gets all the way up to the stratosphere. And when it's struck by a high energy UV photon, essentially, you break off one of these chlorines. This chlorine with this dot next to it, that dot signifies an electron, an unpaired electron. And things react, as you may remember from chemistry, things react to get a full outer shell of electrons. So this has this unpaired electron, so it doesn't have a full outer shell, so it's really reactive. It's crazy reactive, and it wants to react and react. And so what happens is there's this long series of reactions. This chlorine-free radical reacts with ozone there, kind of rips it apart, leaving an oxygen. Then this here reacts with something else, making another oxygen. And the net of these overall reactions is ozone is broken apart and made into O2. And you're stopping that reformation of ozone. So I'm taking ozone concentrations are going down. If there's less ozone, then less UVB is getting absorbed. And that's where we're seeing the human health and the environmental consequences of more UVB reaching animals, plankton, humans on Earth. That's the big problem. That's what happened. These CFCs, 100% man-made substance, solves some great problems, but then made these other, or solve things like refrigeration, which is great, but then made a whole bunch of other problems. And so that's really the concern with them. Now, one of the other things you'll hear about is the problem is the worst in polar regions. In particular, it's actually the worst over Antarctica. So remembering our seasons, okay, when it's summer up in the northern hemisphere, it's winter in the southern hemisphere. And what happens is it's worse in their spring. So in Antarctica, their spring, so we have to think their spring is our fall. Their spring is basically September to November. And in the spring, what happens is it's starting to warm up. And there are things, actually, we'll talk about that in a second. So the problem is the worst over the polar regions. Antarctica, remember, again, their spring is like our fall. And during the spring in the Arctic Ocean is when it's the worst for us. We will mainly focus on Antarctica, though, because the problem is notably worse there. Why? Because it's land rather than water. And so you end up with actually much colder and more concentrated cold to make this problem even worse. They kind of talk about this thing called the polar vortex. So, the polar vortex. If you remember, you've probably remembered some winters where it gets really cold and then they're like, oh, it's the polar vortex. The polar vortex is basically this circulation around the poles. In fact, I'm going to go to the next slide for a moment. And again, it's this polar cell right around the northern pole and then the southern pole. Okay. And it gets really, really cold. And it gets super cold that any of these chlorine-free radicals basically get stuck on ice crystals because the air is so cold. You get a lot of ice crystals just swirling in the air, and these chlorine-free radicals stick on the surface of them. And so that is good because in a lot of regards, it kind of stops thinning of the ozone layer in these polar regions during that time. The problem is then spring comes, it starts to warm up, and those ice crystals melt, which now releases, it kind of like dumps a whole bunch of these chlorine free radicals. And now you get a lot more thinning that is happening in the spring. And so that's essentially one of the big issues where it's a problem because of this polar vortex, and it kind of traps those crystals and then, or traps the free radicals. And then those free radicals all get released at once. And that's bad, but there's even more to it that's a problem because remember, Arctic and Antarctic organisms are very fair skinned, like myself. They're going to burn more. So I'm going to have more thinning there. And I have organisms that are more sensitive, more likely to get burned, more likely to damage their tissues. So that's a problem. And the third problem with that is spring, the growing season. Remember, in the winter, it's almost darkness. It can be 24 hours of darkness in the winter. So the sunlight isn't really reaching that much there in the winter. But come spring, you're getting longer daylight hours. So you have more time for the UV rays to actually reach ground level. And then the growing season is very short, so the organisms have to do a lot to do photosynthesis, or have to do a lot in their very short growing season, which is the spring and summer. And that's when they're getting exposed to the most of the UV radiation, and more of it is reaching the surface because the ozone layer is thinning. This is what I call the triple whammy. I just made up this word, or we've heard the word whammy. There's an old game show that used that idea, but essentially 3 bad things about thinning of the ozone layer. The Arctic and Antarctic organisms are already more sensitive because they're very fair skinned. The thinning of the stratospheric ozone is worse in the early spring and summer. Again, because that polar vortex, as it warms, ice crystals melt and it releases these chlorine-free radicals, making the thinning worse. And then this is an important growing season for organisms there. And the sun doesn't set. The sun doesn't set for some of that time. So they're getting, it's a short growing season, and then the sun is out all the time during that. So this is what I call the triple whammy. Again, why we get so concerned about some of these issues, in particular in the polar region. So that is kind of a nutshell of the sources of CFCs and this idea of why it's so much worse in the poles and why we're concerned about that.